This conference will now be recorded.
Very good evening, students. Today we will be completing this chapter by discussing very important topics. What is paramagnet or paramagnetic materials? Paramagnet or paramagnetic materials? What are the origins of paramagnetism, and magnetic hysteresis, BH loop, soft hard magnetic material, their uses, etc. Okay, so first of all, let us discuss about paramagnet and its origin and some of its examples. Okay, so as you know, uh, first of all, let us discuss few properties of paramagnet. Okay, so few properties of paramagnet. So paramagnetic materials are those which develop weak magnetism or weak magnetization in the direction of applied magnetic field. Okay, so I hope you remember this. What is magnetization? Let me just tell you magnetization. This we have already discussed, but still I'll just recap for a reason, because we need to know this definition very well. So this is actually net dipole moment. This is the ratio of net dipole moment, net magnetic dipole moment, net dipole moment per unit volume. Okay, suppose you have a magnetic substance and you have magnetic dipole. Magnetic dipole moment, we just give such just an arrow. Okay, that means there is a magnetic dipole which has a magnitude and direction along this direction. Okay, like this, along this direction. Okay, so I may have a substance which where there could be many magnetic dipoles. Okay, of the order of 10 to the power 23 maybe. Okay, there could be many magnetic dipoles, but see, all the dipoles may not be in the same direction. The magnetic dipole moment is denoted by m vector, so it is a vector quantity. So why this net term comes? Net term comes here since this is a vector quantity. So within this volume I may have all sort of directions of this magnetic dipoles. Okay, like this and all like this. Okay, so all sort of directions I may have. So I need to find out magnetization. Okay, net magnetization or net magnetic dipole moment here, so that we get magnetization. So I should take see, if I want to calculate magnetization in this direction, then I should take component of all these magnetic dipole oriented in different directions along the preferred direction. Okay, see, I just would like to find out magnetization in this direction. Okay, magnetization is also a vector, so I need to take component of all this dipole moment along this direction and perpendicular to this. Okay, all right. So there are all sort of like orientations of these dipoles or dipole moments. So as many you have, you can take the component of all sort of components and then add them up along this direction, so that you get net dipole moment along this direction. Okay, so that is actually called net dipole moment, and then you just divide with the volume of the substance, then you get the magnetization. Okay, this is how magnetization is calculated. So it is said that paramagnetic materials, in case of diamagnet, if you remember, we have seen magnetic dipole moment, they are oriented in the opposite direction of the applied field. That's how we get chi minus. Okay, some minus quantity, negative quantity, magnetic susceptibility. That means it opposes the external field. So diamagnet opposes the external field, and it produces a negative magnetization, and that negative magnetization is very, very tiny compared to paramagnetic contribution or ferromagnetic contribution in a substance that has a very, very small value. All right, and we have seen perfect diamagnet. Example for perfect diamagnet is a superconductor. Okay, superconductor. So here we have understood what is magnetization, how we calculate magnetization. Now we'll see in case of paramagnet, it is actually opposite compared to the diamagnet. See, suppose I have such a material where all sort of orientations of dipoles are there. So I have a very feeble or weak magnetization along a preferred direction. Weak magnetization. In general, what we do in case of paramagnet, we will discuss very soon during the discussion of origin of paramagnetism. So what happens in case of paramagnetic material, when we place that paramagnetic material in a magnetic field or magnetizing field, if you apply magnetizing field H, then it develops weak magnetization. That means the dipole will have a very small contribution along the field direction. Okay, so that is what it means. Okay, so at least here the field is not opposed by the magnetization. Okay, magnetization is denoted by M actually. Okay, M vector. So in case of paramagnet, magnetization or magnetic dipole moments are not oriented against the direction of the field. They are oriented in the direction of the applied field itself, but contribution of the dipole moment along the field direction is very, very weak, so or very, very small. That's why very weak magnetization is developed when a paramagnetic material is placed in an applied field. Okay, all right. Now second point is that paramagnetic materials are weakly attracted since it has very weak magnetization. So it is actually weakly attracted by a magnet. And see, if I have non-uniform magnetic field region, okay, non-uniform magnetic field region, if I keep this, so somewhere non-uniform in the sense somewhere strength of the magnetic field is very, very high, strength of the applied magnetic field, and somewhere strength of the field. As you know, the field lines, dense field line means strong magnetic field, strong, and here it is weak, applied field is weak. If we place a paramagnet somewhere here, paramagnetic material somewhere here, it will have a tendency to move towards the or attracted towards the strong magnetic field region. Okay, it will move from weak magnetic field region to strong magnetic field region. This is what the second point is meaning. This is another property of a paramagnetic material. So if we place a paramagnetic material in a non-uniform magnetic field, it has a tendency to move towards the stronger field region from the weaker field region. All right. Okay. Now next property is that, okay, these are example like manganese, even magnesium also. Manganese, chromium, aluminium, sodium, oxygen. These are all actually paramagnetic substances. See, oxygen is gas, sodium solid anyway, chromium, these are all solid. So among the gases, oxygen is actually paramagnet. See, this is among the gases. So among the gases, oxygen is a paramagnetic substance. Okay, so at STP, these are some paramagnetic material. Okay, so you will be given in exam some examples, like say maybe chromium will be given. You will be asked to find out which one is paramagnet out of 5 materials. Among them, if chromium, aluminium, or sodium, oxygen, manganese are seen, any one of these is seen, then you can just choose that. Okay, all right. There may be many other, not maybe, there are many other paramagnetic substances. So you can see from textbooks or somewhere to get many more examples of paramagnetic substances. Okay, all right. Now another point is that, see here, magnetic permeability, you know, this is magnetic permeability. Then we have relative magnetic permeability. Then mu zero is actually permeability in free space. Permeability, I have already discussed what is permeability. I'll tell you what is the meaning of that again. This is called relative permeability. Permeability. Sorry, I think permeability, Lity. This is simply permeability, magnetic permeability. There is actually permittivity in electricity. Counter quantities in electricity are this: epsilon, epsilon r, then epsilon zero. Epsilon is inside the material. This is relative permeability. Sorry, relative permittivity, and this is permittivity in free space. Permeability. Okay, now let us see the meaning of permeability or relative permeability. Okay, suppose I have a material here, and I'm just keeping this material. This is some magnetic material. Some magnetic material. See, in general, one thing you have to understand, that magnetic material doesn't mean that it will show the magnetic property at any condition. Okay, it is not true. Okay, you have iron. Iron is a very good ferromagnetic material, but it will not show magnetic property unless you place inside a magnetic field, or unless you bring it near a very strong magnet. Okay, it will not show the magnetic property. You know that, like you have some iron balls. If you bring near a strong magnet, bar magnet, then they will be attracted. That means they got magnetized. But if you have two iron balls, they don't attract each other. So I'll tell you the reason there. So magnetic material doesn't mean that they are magnet. They have to magnetize by externally applied magnetic field, or by bringing them near to a very strong bar magnet. Okay, now one thing you have to see, this is a magnetic material. So once we keep them inside external magnetic field, then how do they allow the external magnetic field to influence it? Or, see, magnetic field is characterized by magnetic field lines. So how many magnetic field lines this magnetic material allows? That is the quantitative measure of permeability. That is the quantitative measure. So suppose I have 5, or maybe I have, so I have some 5 field lines over here. So if it allows only one through them, then it has weak permeability. It doesn't have much permeability. If it allows more than one, or maybe much more magnetic field lines to pass through it, then it is having good permeability. That means it is actually giving permissions to the external field lines to pass through it and influence itself. Okay, so this is the thing, permeability. Permittivity is the same thing. So the medium which has greater permittivity will allows more electric field lines, or will be influenced strongly by the external electric field. So here also the same thing. If there is a good magnetic material, then that will be strongly attracted by a bar magnet, or it will be easily magnetized or strongly magnetized by externally applied magnetic field. So that is actually permeability. Permeability means how much permeable it is, how much how much uh, cooperative you can say, or how much permission it gives to the external field lines to influence it. So that is actually permeability. So in case of diamagnetic materials, what we have seen, I'll just draw now. See, dia and para will show later, dia, para, ferro together. So suppose the diamagnetic material is there, it is kept in a inside a, like in a uniform magnetic field. See what happens, it expels. Expels means it repels the magnetic field lines. Okay, it repels. Hardly one field line may go through it. Okay, it repels the magnetic field lines to pass through it. It repels. This is called expulsion. So diamagnetic material does not allow magnetic field lines to pass through it. So that's why it is said that its permeability is less than the permeability of free space. So free space allows more magnetic field lines than this magnetic material, diamagnetic material. In case of paramagnet, what happens? It actually, paramagnet is little better. It allows few lines to pass through it, but it does not expel, or it does not at least it does not repel the magnetic field lines. But anyway, it also has very not very significant permeability, but still its permeability is greater than the permeability of the air. Okay, so it can allow more magnetic field lines than the air medium. Okay, so this is the thing. Okay, this is the last point here I am discussing. So permeability, the paramagnetic permeability is greater than the magnetic permeability in free space. This is mu0, and thereby the permits magnetic field lines more inside the material than in the free space. Okay, all right, this is mu0. I have one more point. Magnetic dipoles are independent of each other, or they do not interact with each other. This part I'll discuss while discussing the origin of the paramagnetism. Okay, so let us see what is the origin of paramagnetism. See, in case of paramagnetic material, they have already permanent dipole moment. Permanent dipole moment due to spin. Okay, so I'll just write one by one. So paramagnetic material already has permanent dipole moment. Okay, permanent dipole moment. Just a minute. See, this theory was given by, first of all, let me write. This theory was given by Langevin. Okay, this is called Langevin's atomic theory or molecular Langevin's theory. It is called Langevin's theory. It is Langevin's classical theory. It is called Langevin theory of paramagnetism or atomic magnetism. Okay, so Langevin, according to Langevin, atoms or molecules of paramagnetic materials possess a permanent magnetic dipole. I'll write few terms here. Permanent, so possesses permanent magnetic dipole moment. See here, these are atomic dipole. See, these are this. So they have all atoms. See, these atoms are having net dipole moment. So this arrow, red arrow is. So these are atoms. These are all atoms. I did like these are all different atoms, and each atom has a net dipole moment. These are called actually atomic dipole. Okay, or atomic dipole moment. And these are permanent. That means, and why why these are arising? So these are actually the dipole moment arising moments are arising due to unpaired electron. Okay, this term you will understand later. So due to unpaired electron, a single electron has its spin. Okay, its spin. So this is actually, this paramagnetism is originating from the electronic spin. Okay, electronic spin or unpaired electron. So paramagnetic substances possess permanent atomic dipole moment due to unpaired electron spin. Okay, or electronic spin, or simply unpaired electron. See, even though there are permanent dipole moment, still we get zero magnetization when we don't apply any external magnetic field to magnetize this paramagnetic substance. Why? Because see, inside any substance there is some thermal energy, that is kBT. This is thermal energy. So this thermal energy is related to the fluctuation, or we would say thermal. This is called actually thermal agitation. Because of this thermal agitation, their orientation. See, this dipole, these are vectors, right? So their orientations are very random. Okay. In absence of field, or H I am writing, applying or magnetizing field, the dipoles are randomly oriented. Why? Due to thermal agitation. This is called thermal agitation. This is some kind of energy which agitates this dipoles not to stay in a single direction or single configuration. Okay, its configuration changes continuously. So this ceaseless random orientations of this dipoles, permanent dipoles, results in zero magnetization in absence of applied field. Okay, so this is the reason permanent magnets are very weak initially, or maybe there will be, and obviously there will be zero magnetization in absence of field. But when you apply external magnetizing field, all the dipoles will actually gain energy to oppose this agitation, thermal agitation, or to overcome this thermal agitation, and they are oriented along the direction of field. Okay, so what I said, they have like paramagnetic substances have their permanent atomic dipole due to electronic spin or unpaired electrons, but in absence of field, dipoles are randomly oriented due to thermal agitation, making net magnetization zero, making net magnetization zero. Magnetization zero. So when an externally applied field is there, then this dipoles actually gains energy. The dipoles gain energy to overcome this thermal agitation cavity energy. Okay, and then they try to orient themselves along the field direction. This is called alignment of the dipole along the field direction, and then magnetization develops. But see, this is actually the final stage when all the magnetic dipole will align in the same direction along with the, like in the direction of field. This is actually at very high field, at very high field, at very high field, as high as 10-20 Tesla high field. Okay, high field, at very high field, maybe some 14 Tesla, 20 Tesla. Okay, to get this kind of configuration. So this configuration, when all the dipoles are oriented along the field direction, this is actually called saturation. After achieving this saturation, even if you increase the field, suppose it has reached this configuration at 15 Tesla applied field. Now if you increase the field to 18 Tesla or 20 Tesla or maybe more than that, then you are not going to get more magnetization, because all the dipoles available in the substance will already has contributed to the magnetization, and no longer new magnetic dipole will come and align along the field direction to give rise to increased magnetization. Okay, so this condition or this situation is called saturation, and the magnetization we get at this stage is called saturation magnetization, m suffix s. Okay, so this is the origin of paramagnetism. So what is the main origin of paramagnetism? That is the permanent dipole present in the paramagnetic substance due to unpaired electron, or you can say permanent atomic dipole due to unpaired electron. Okay, so that is the origin of paramagnetism. Okay, how we get magnetism then? By applying external field. Okay, so what happens when we apply external field? All the dipoles slowly start aligning towards the field direction. Okay, and at very high field, the all the dipoles maybe will be aligned to the externally applied field, and at this stage, if you further increase the field, magnetization will not increase. So that particular magnetization is called saturation magnetization. I'll show you in graph. Okay, first of all, let me tell you what is Curie law. Okay, so Curie, you know, famous Curie. So he actually, I think I'm actually, yeah. So I think it is he who has given the first law for magnetism. Actually, not only this is for paramagnetism, obviously Curie's law for paramagnet. So actually what happens, I'm sorry, I'm just actually confusing with he or she. Curie, there were Marie Curie and Pierre Curie. I'm confusing with uh, which Curie. Okay, I'll just tell you later which Curie, C, whether it is she or he. So experimental results suggested that magnetization of a paramagnetic material is directly proportional to H. Actually, Curie, from experimental results, she could understand that magnetization is directly proportional to the external field, and it is also inversely proportional to the absolute temperature. Absolute temperature. Okay. So according to Curie's observation, experimental observation, magnetization was found to be directly proportional to the applied field or field intensity, and also it was found to be inversely proportional to the temperature. Generally, this part is called Curie's law. Okay, and so we will show you here how paramagnetic susceptibility vary with temperature. So here, see, combining these two proportionality, I can write this by H by T. So let us take a constant. Okay, this is called Curie constant. Okay, this is called Curie's constant or Curie constant. Okay, Curie constant, because this law was given by Curie from the experimental results. So Curie C H by T, and we know susceptibility, magnetic susceptibility is M by H, right? So M by H means it is C by T. So this is actually known as Curie's law of paramagnetism. Curie's law of paramagnetism. Paramagnetism. See, I have just forgotten to mention you here one property you had seen, that there are permanent atomic dipole in paramagnet, but one thing you remember, that these are very selfish guys. See, these dipoles are very selfish guys. They actually just think of themselves. They do not interact with one another. Okay, so that's why they are called independent dipole. Okay, they are called independent atomic dipole. They don't interact with each other. Okay, so this is the case in case of paramagnet, but we will see in case of paramagnet. So some of the dipoles will interact with each other. Okay, so this chi versus T is plotted here. This look like this. Okay, so chi versus T for paramagnet is this. Okay, for paramagnet, this is actually the graphical representation of Curie law. Okay, Curie law of paramagnetism. Graphical representation. Okay, so this is one thing. So here at some time there will be questions actually, because from this particular Curie law. We'll just take up numerical problems. That time we'll discuss how questions come, how questions are asked based on this Curie's law. Okay, so Curie's law, I have told you Curie's law. So chi is equal to C by T. So this is Curie's constant, and this is absolute temperature. This is actually absolute temperature in Kelvin. So Curie's law we have already learned. And see, here I was talking about saturation magnetization. Saturation magnetization. So saturation magnetization is, see, the situation is here. Saturation magnetization is, this is the situation of saturation magnetization, when all the magnetic dipole, atomic dipole are oriented in the field direction. Then even if you increase the magnetic field, applied magnetic field, there is no increase in magnetization. Look here. See, this is the region of saturation when you are, this is obviously with temperature, that's why it is okay. So this is with temperature. So at certain temperature and at particular field, it will be saturated. After saturation, see, it will actually be constant like this. Okay, it will not increase further like this. So that is saturation. And the magnetization at the saturation state is called saturation magnetization. That is denoted by ms. So this is Curie law, this particular term. So okay, so yeah, so this is the thing. All right, so we'll go to ferromagnetism. So here also we'll learn few properties of ferromagnetism. As you have seen in case of paramagnet, we'll discuss few properties of ferromagnet also. See, in case of ferromagnetism, ferromagnetic material develop strong magnetization. Okay, so ferromagnetic, I'm writing FM, ferromagnetic material. Okay, ferromagnetic material for FM. FM, I'm just writing once here. FM, ferromagnetic material. Okay, ferromagnetic material. So FM develops strong magnetization. We have seen diamagnet develops, it opposes the external field, it develops very weak negative magnetization. In case of paramagnetic field, paramagnetic material, we have seen they develop positive magnetization but weak magnetization. But ferromagnetic material actually develops strong magnetization. Okay, strong magnetization. All right, in the direction of field and also in the direction of field, in the direction of applied field. Second thing is that they're attracted FM substances. Okay, FM are attracted strongly. Okay, strongly by magnets. Okay, strongly by magnets. Then third point is that FM materials have tendency to move towards strong field region if we keep it in a so FM have tendency to move towards strong field region from weak field region. Okay, here see FM materials have permeability much greater than mu0, as good as, see, they have relative permeability as good as, in case of iron it is something like 1000. Okay, what is relative permeability? Relative permeability is this, mu by mu naught. This is relative permeability. So ferromagnetic materials have large uh, permeability. That means, you know, if you keep three materials, like this is dia, this is para, this is ferro. So ferro will actually allow more magnetic field lines to pass through it. It will be allowing some, and it will be hardly one. This is dia, this is para, this is ferro. Ferromagnet will allow more magnetic field lines passing through it. So some examples are there. So what are examples? Like iron examples. Okay, so ferromagnetic examples of ferromagnetic material: iron, nickel, then cobalt. Okay, these are few examples. Okay, so generally these are high temperature ferromagnet. Okay, naturally occurring ferromagnet, in the sense they can be easily magnetized and strongly magnetized at room temperature itself. Okay, so these are properties of ferromagnet. Now we'll see what is the origin of paramagnetism. So this is very, very interesting to learn here. So what is the origin of paramagnetism? See, there was scientist called Weiss. So Weiss explained paramagnetism, explains ferromagnetism with domain theory. Okay, domain theory, by domain theory. I'll tell you what is this domain theory in brief. See, in earlier case, we had seen there were atomic dipoles, right? And they are independent of each other. That means they don't talk to each other. They don't talk to each other. They don't cooperate with each other. They don't help each other to find a find a suitable configuration. But here, the dipole in case of ferromagnetic material, these guys are very, very cooperative to each other. So atomic dipoles are actually very, very cooperative. They interact with each other. They actually go together. Inside a magnetic material, according to Weiss, there are small macroscopic region. Okay, small macroscopic region, as you see here, where these atomic dipoles are very, very cooperative, and they actually go, or they orient themselves in a particular direction. See, this is the region. So this is the region where three atomic dipoles are orienting in this particular direction. Okay, this is a region like this one. There are three dipoles again which are orienting themselves in a particular direction. So these dipoles or atomic spins, okay, the electronic spins here are cooperative, so they interact with each other. Okay, so here also atomic dipoles are there, but these dipoles are not independent of each other. They are actually interacting each other, and they have cooperative interaction. Okay, cooperative interaction. I'll just write in brief. So permanent dipoles are already there. So permanent atomic dipole, I think, okay, so permanent atomic dipole are existing here. Okay, atomic dipole exists. Okay, then dipoles are interacting, not independent. Okay, they depend on each other. Dipole are interacting. Okay, so what happens in a particular region? Dipoles are cooperative to each other, and they orient in a particular orientation, or in a direction together, and those particular regions are called actually domains. Okay, so domains Domains are there. Okay, domains are, so these are actually macroscopic regions where all the spins, all the dipoles orient themselves selves themselves in a particular direction, direction, or in the same direction. Or you can say that in a particular direction. You know, these regions are called domains, and they have, say, wall thickness. They have, I think they have thickness of the wall of 1 millimeter thickness of the wall. Let me just check once. So typically thickness of the domain, that means this thickness or this thickness of the wall. Okay, domain thickness. I'll just complete this after discussing this origin of paramagnetism. I'll just stop today. Next day we'll continue with BH loop and magnetic hysteresis and applications of BH loop. Domain thickness. Domain thickness is 1 millimeter. Okay. And how many dipoles are there in a single domain? Of the order of 10 to the power 11 or 12. Okay. This many numbers of dipoles are there. Dipoles. Okay. But in absence of, see, even though domains are there, along a domain there is a net dipole moment. See, they have net dipole moment along this direction. This have this direction. This will have this direction. This will have in this direction. This will have in this direction. This will net dipole moment, because all of them will add up. So resultant dipole moment will be like this. Look, even though in a single domain, magnetic dipoles are orienting themselves in a particular direction to give net dipole moment, but still, see, if we see overall, this see, this dipole moments, like net dipole moments of each domain, they are actually randomly oriented due to this thermal agitation again. So due to this thermal agitation, these domains are not oriented in a particular direction. They are oriented in a random direction, as you see here. Each domain will have net dipole moment, as I showed, but net dipole moments will be oriented randomly due to thermal fluctuation, okay, or thermal agitation. But as soon as you apply a magnetic field, the domains will try to orient themselves towards the field direction. Okay, see, this domain will rotate. First domain will rotate, and then domain walls will actually get, see, you know, finally. So this, I think this figure is not very scientific. Or see, finally, when at very high field, all the domain wall will actually be vanished, and all the dipoles will be in a single domain, giving a net direction, or all will be directed in the same direction. So this will be actually the ultimate configuration. Actually, after orienting all the dipole moment, after orientation along this same direction, further that this domain will not be there. Actually, all will be in a single domain. So you will see this as single domain. Okay, single domain. Okay, I think I have got this figure from the textbook itself, but it may not be. Anyway, you will learn this in higher classes again, that when all the walls, like all the walls will be actually vanished, all the dipoles will be, atomic dipoles will be oriented in the same direction. This is also called saturation. Saturation in the sense you will get the maximum magnetization, okay, out of this. Like when you have like in particular, so not only the field, you can control this orientation by, or magnetization, control the magnetization with temperature. So magnetization is a function of temperature, magnetization is function of applied field. Okay, so these things are there. So when you apply sufficiently large field, then you know all the domains will be merged to a single domain to give rise to saturation. Okay, and then you will get highest magnetization. So this is how. So what is the origin of paramagnetism? That is explained by domain theory by Weiss. Okay, then we'll learn there is a theory called Curie-Weiss law. So according to Curie, above certain temperature. Okay, I'll just discuss that properly in the next class. All right. So thank you for your patience. Bye for today.